Okay, so we just got done talking about how you can alkylate the alpha position of a ketone by treating it with LDA at low temperature to generate an enolate, and then reacting that enolate with an electrophile like methyl bromide, which will alkylate at the C side of that enolate at the alpha position to generate this product. Now, what if we took this product and we wanted to run the same thing? We treat it with the same conditions, so we start with this ketone instead. And let's go ahead and draw on that methyl group. The thing to note is now we have two different types of alpha hydrogens, right? We have these red ones over here, and we have this blue one over here. They're not the same. They're not equivalent. So which one of those is going to get plucked off? Well, we have to remember that LDA is a bulky base. Now, that is good for two reasons. Its bulk means it's not nucleophilic. It's not going to add to the carbonyl group, so we don't have to worry about that. The next thing is that we're going to use it as a base, and it's going to pull off the protons that are more sterically accessible. LDA is a much stronger base than an enolate is. Once it rips off a proton, it's not going to give it back. We're not going to establish an equilibrium. So it's going to pull off the more sterically accessible protons first, one of those first, and not give it back. So what we're left with, the enolate that we end up generating, is this. This methyl group is still over here. And when we react that now with the electrophile, that's going to install that methyl group on the other side of the carbonyl group from the original methyl group there. So we get this product here. Now the question is that we want to ask ourselves is, would there be a way to generate this product, having both methyl groups on the same carbon? And the key thing that we need to think about when we're doing this is the enolate that would have to come from would be this one. And the key things to note about this are that in order to generate this enolate, we're going to have to pull off this hydrogen. The blue hydrogen is the one that would lead to that. It's the more sterically hindered proton. So how could we access that? Well, it's probably not going to be by speed, but it's going to be by thermodynamics, by reaching an equilibrium, because of this enolate is more stable thermodynamically than that enolate. And the way we could explain this is that this enolate has this extra methyl substituent, so this double bond is more substituted. And we talked previously about how more substituted double bonds are more stable. So this enolate is more stable than that one, but is there a way that we could establish that we can get to this equilibrium? The answer is yes. And funnily enough, we're going to end up doing it using the exact same reagents as we did before. We're just going to tweak the conditions a little bit to favor reaching an equilibrium. So that's the same starting material. And what we're going to do this time is we're going to treat it with LDA again, but we're going to do it at a little bit warmer temperature, and we're not going to use a full 1 equivalent of the LDA. We're going to use a little bit less than there is that starting ketone. And what this is going to do is it's going to favor the generation of this enolate. Now, why is that? Let's think about it. Well, if we're reacting with 0.95 equivalents of LDA, what's going to happen is that the starting material is going to be converted to what? Well, the LDA is still a bulky base. And the protons, and strong, the protons it's going to pull off it's still going to favor pulling off these less sterically hindered protons. So that's what we're going to get originally to start out. We're going to end up getting the exact same enolate as we did before over here. But we're only going to have 95% at most converted to that. We're still going to have, because we have an excess of starting material, we're still going to have some starting material left over. Now, had all of the starting material been converted to this enolate, we wouldn't be able to establish an equilibrium because of this enolate. The proton over here is no longer acidic once you've deprotonated from the other side of the carbonyl group. This proton over here is not as acidic as it was in the original starting material. But if we have excess starting material, then this enolate could deprotonate some of that starting material either over here or there to generate a new enolate. Now, if this enolate were to deprotonate either of those two hydrogens, it's kind of like a non-reaction. It would just generate, this would turn into the enolate, and then the enolate would turn back into starting material. So it wouldn't be productive. But occasionally, what we're going to have is that this enolate is going to pick off that hydrogen. And when it does, it's going to generate a different enolate. And what we're going to see from there is that the enolate that's generated from that proton transfer is going to be this. And we talked about how at equilibrium, this enolate is going to be favored, this enolate is going to be favored over that one because this is the more stable enolate. It's more substituted. So given enough time and a little bit of a higher temperature and an excess of starting material so that we could establish this equilibrium, we're going to get to this enolate. And then once we react that enolate with the electrophile, that's going to give us the other product. So you can, using the exact same reagents, LDA and methyl bromide, methyl iodide, wherever you want to use as the electrophile, you can choose what side of an unsymmetrical ketone you want to alkylate.